Hi everyone, and welcome back to the second lecture in understanding paleoclimatology. Sort of that the past 2.5 to 3 million years of temperature, and how we use proxies and everything to reconstruct that. Fun fact for the day. This is obviously super related and not just a random fact, but I always like to think about these past climates in very real ways, tangible ways. Like how can I really envision what these past climates may have looked like? And to me, it always helps to look at a map, right? And I like this one. This one's really simple. It shows all of those Pleistocene era lakes. So this is, remember the Pleistocene was like 2.6 or 2.7 million years ago to about 20,000 or 15, actually, I think just even like 12,000 years ago is when the younger dryas kind of hit us. And then we transitioned into the Holocene. So this is a long time, and these lakes and these water bodies definitely waxed and waned. But just imagine, right? Like most of us are from the West. We all kind of have a good concept of sort of how dry most of the West is, and except for in the far Pacific Northwest. And so, I mean, especially for those of us who are familiar with like Nevada, I mean, so we had lakes all over the place. This is called the basin and range because basically every valley was full of a little bit of water, which is cool. But we had this massive Lake Lahontan that was huge, extended way up into Oregon. I mean, just a massive Great Basin lake. This is why we have the Black Rock Desert up here, because it's the lake bottom of Lake Lahontan from the Pleistocene. But just as a comparison, right, there's Tahoe and there's Pyramid Lake. So Pyramid Lake was actually part of Lake Lahontan, huge thing, fed by the Humboldt River. At some point, it's thought that it was connected to Lake Bonneville. Lake Bonneville was massive compared to the Great Salt Lake, and we think the Great Salt Lake is huge. But I mean, all those salt flats that you drive through, if you've ever driven I-80 out here in your way into Salt Lake City, it's just amazing, right? Like this is all Lake Bonneville. And those of you who've been down to Death Valley, either with our eco adventure or otherwise, this is like Manly. This is like so the Badlands of Death Valley are the remains of an old ancient lake, a Pleistocene lake, and it's shown right here. And it's interesting. All the local Native American tribes, they have a deep oral history about this. It's pretty cool. And I mean, there's just like thousands and thousands of people who lived along Lake Manly back in the Pleistocene, towards the end of the Pleistocene. And so just cool to kind of think about these things, right? The Central Valley, the reason why it's so lush and fertile is partially because it's an old riverbed or lake bed. Just cool to think about just how dramatically different this place was, especially when it comes to water. So random fact for the day, or fun fact for the day, not super random. Okay, so remember we're talking about proxies and which are just anything that can kind of be used to represent the value of something that you can't directly measure. And in climatology and paleoclimatology, I kind of introduced you to pollen and marine eukaryotes and coral and chironomids and sediments and tree cores and ice cores and macrofossils and all kinds of things. I didn't mention one thing though, which is geology, right? So, I mean, just the physical landscape is shaped and gives us all kinds of clues of past climate. We have, these glacial moraines where it's very obvious that ice carved this landscape. And because that exists, we know that, certain things like last glacial maximum existed. And we see this evidence, worldwide. These debris fields from glaciers, massive boulders in the middle of fields, right? Things that simply couldn't be put there except for massive forces like glaciers. And so we have this evidence on the physical landscape. It doesn't take a lot of imagination to start to put that together and paint a picture of the last glacial maximum, right? So this shows a little bit of what we saw before. It also shows some temperature data, proxy data kind of on top of it as well. I like this one a little bit better because it shows, the glaciers, it shows, the massive ice sheets, but also shows sort of the resulting environments that are created by the glaciers. Because you imagine, glaciers are mostly up here in the north now, right? You realize, I mean, if you haven't been to Alaska, you may not realize, but right adjacent to the glaciers are these polar deserts, right? So that was what characterized most of Washington and northern Oregon during the last glacial maximum. And again, we have lots of evidence to suggest these things. We have regular fossils, we have the rock fields, we have all kinds of stuff to kind of paint this picture of like this was sort of the extent of it. We have all the lake bottoms to kind of represent all those Pleistocene era lakes. There's a lot of evidence just on the physical landscape of these dramatic climate changes. And we know that this can't exist under certain atmospheric conditions. We cannot recreate this in any kind of model unless we reduce the amount of CO2 and we account for things like Milankovitch cycles. So hopefully you guys have heard about this before. This isn't too new, but remember the Milankovitch cycles have 3 different cycles working in tandem. So there's some episodic nature to it, but it's not it's not a consistent cycle, right? It's not consistently episodic. You've got 3 independent cycles operating at different timescales. So you have the eccentricity, caused by the fact that we have other planets and other celestial bodies kind of pulling us and tugging us in different ways, right? So we don't have a perfect circular orbit around the sun. We are influenced by other celestial bodies. We have the tilt of the Earth, which right is largely driven by gravitational pulls as well, but also the ocean shifting and things like this, density of the ocean, all kinds of stuff. And so we shift around the Earth's axes, and that causes increased warming, decreased warming. So does this. If we're far away from the sun, we're obviously going to be cooler than if we're really close. So we have this big long cycle, we have these shorter variations, and then we have these even shorter precessions. Which is really just a wobble, and that's associated with just the relationship between the tilt and the eccentricity. So I have another little animation for that. I kind of like this one just because it puts it all together, right? So we have the eccentricity, which is longer time scales, 100,000 to 413,000 years. We have the precession, which is only every 26-ish thousand years, and then we have the tilt that changes every 41,000 years-ish. Again, it's kind of constantly moving, right? So those of you who've taken maps of photography kind of might remember like the magnetic poles move around. The North Pole moves around. This is why magnetic north is sort of tricky, and why you don't want to rely on old topo maps, because the declination between true north and magnetic north probably shifted. Sometimes it shifts a great distance, and that's all related to the slight change in tilt. So all kind of cool, but I mean, imagine all of these things kind of working in tandem. So if you have a tilt, sort of close to the sun, and you happen to be on the orbit closer to the sun, but the tilt is only for like half of it, right? So in this case, the northern hemisphere is sort of tilting closer to the sun, and the southern hemisphere is not. Well, obviously, we're going to see a lot warmer temperatures on the Earth's surface, versus if we're out here and the northern hemisphere is tilting away from the sun, and we're kind of far away from a traditional or the previous orbit, or a more circular orbit, then the northern hemisphere is going to be really cool, and southern hemisphere is going to be cool too, but not as cold as the northern hemisphere, because we're simply not tilting that way, right? So pretty major differences here going on, caused just by the Milankovitch cycles. And I like this shows that precision kind of nicely, right? So if you imagine this wobbling too, the axis is actually changing a little bit in addition to this rotation around on a top. And it just kind of gives this nice illustration of how the position of the Earth, and it's nice too, it has the sun versus the shade, right? How the position of the Earth and just how it's tilting and where it is on this rotational axis, as well as the orbit, is either going to increase our exposure to the sun or decrease the exposure to the sun. And remember, all of our heating, all of our energy comes from the sun. So these kind of shifts make a huge difference in climate. And we see that, right? So we look at these cycles and we think about the eccentricity, which we can model pretty well. We can think about the tilt, which we can model pretty well, and we can think about the wobble, which we can model pretty well. And you combine that together and you get the really nice, clear picture of, okay, when are we expected to be warmer? And when are we expected to be colder? And this is what drives those glacial signals that we saw in the chapter and everything. So let's talk about merging these proxies. Oops, this unfortunately got cut off. This was supposed to come in as an animation. So, so when you take into account, so say like, you know, the glacial maximum, I'm going to skip ahead actually, because this is the one I wanted to talk about first. When we talk about the glacial maximums, and we talk about the Milankovitch cycles, that we can start to kind of piece together these really you know, interesting variations that we see in the record, climatic record. So, you know, these cycles that we see here are going, they're at that time scale. So this is back to 800,000 years ago. So this is time in thousands of years before present. So 800,000 years ago. So that's plenty of time, right, to pick up these Milankovitch cycles, especially the precession and the tilt Milankovitch cycles, pieces of the Milankovitch, but even the eccentricity kind of stuff, we are picking these up and you see these large swings. And so this corresponds very well to the Milankovitch cycles. And when we're talking about merging proxies, these are three different proxies telling us the exact same story. So this is really, really key. And this is where the consensus, climate consensus, starts to make a lot of sense. When we start to look across all these proxies. So this one is Antarctic temperature driven by, I just forgot for some reason, the temperature anomaly estimated from the deuterium ratios, right? So this is the heavy hydrogen isotope, similar to the oxygen that I talked about in the book. So you've got a reconstruction based on isotopes up here, hydrogen isotopes. You've got a reconstruction here from CO2 concentrations from ice cores. And then you have reconstruction here of the heavy oxygen isotopes, estimating global sea level changes. And we see the same pattern. So this is the wiggle matching that I was talking about. So we have a wiggle, we see the cyclic nature, and it's like, wow, that is like wild, right? We're seeing pretty big fluxes in temperature going back 800,000 years. You compare that to CO2, it's like, wow, that's wild fluctuations. And hey, look, like it's really, really close to what we're seeing sort of in these temperature anomalies. And hey, it looks really close to like global sea level changes. And hey, this all matches up with what we understand about Milankovitch cycles. So that's a lot of science compiling. And this is like, you know, traditionally discrete science, right? We would not necessarily be comparing all three of these things 100 years ago. We just wouldn't have thought about it. But now we can. We can line this all up. We can think about it in the same time period, and that's really, really huge. And so going back to this one, right? So you know, looking at the Marcotte et al. from the Science journal, they really spent a lot of time thinking about, okay, let's pull all these proxies together, and they did almost everything. I think I've got a map of it in a second, but everything they could put their hands on for describing the Holocene, basically. So it goes back to about 11,000 years. So that's the transition from the Pleistocene to the Holocene, and the Holocene is what we're considered to be in until recently, when we decided, you know, look, we're way outside of the Holocene, and that's actually what this is showing right here. But they went through and they looked at every possible proxy, all the things that I was talking about in the last lecture. They looked at all the possible proxies, age adjusted them, you know, did some really good reconciliation of the different radiocarbon date estimations so that they're all consistently derived, and plotted this out with the confidence intervals. And so going all the way back to 8,000 years, we see a really nice amount showing up there, or a really nice trend showing there. And then from the last 2,000 years, this is kind of where the graph cuts off, sorry about that. you see this, again, it's the temperature anomaly graphs. You see this kind of steady kind of fluctuation, but consistent, and then it just spikes upward. And this is inconsistent with all the other forces happening in the Holocene. And this is why we call it now the Anthropocene, because we see this. And so his reconstruction, the science Marcotte reconstruction, is in blue. The red is the global temperature anomalies as measured by modern instrumentation. So it's a different line. And we see the from the late 1800s. And yeah, you're going to get finer resolution for sure. But the key here is that it's the same trend, right? So while the paleo evidence doesn't capture this huge drop in the late 1800s, that's largely because it's not paleoid, paleofied now, right? It's not been preserved. A lot of the stuff from the 1880s, 1890s, 1900, that's kind of harder to sort of reconstruct in the same way that we do the 2,000 and 3,000-year-old stuff. It's not perfectly preserved at this point, right? It's still being sort of fossilized if you think of that about the amaranths. So so we get higher resolution certainly with modern instruments, but the trend is still the same. And then you compare it to things like this Pages 2K construction, which is yet another effort. And again, the magnitude is a little off, but it's only 0.2 in terms of anomaly, though that is certainly something to consider. But it's the same trend, right? We have kind of variation around the mean of the current, just average temperature, drop a little bit through the last little ice age, right? That kind of defined Europe, and then we just shoot off the chart almost. So let's look at that 2K. Yeah, let's look at that 2K stuff. So we've got the 2K pages, or this Pages 2K network is really trying to better understand, global climate. And so they've gone through this really nice as a poster they just put together for the American Geophysical Union this last month, I guess. And they kind of go and they talk about all the different data sets and all the different proxies that they look through to kind of combine this crazy data model that you saw on that previous graph. And there's distribution of sites. And I was looking for this actually for an exercise on Tuesday, and it just, another website's quite worked out. But there's this really cool effort going right now that looks across all these data, provides a repository for all these data sets and allows you to map them and tell you what each site represents, what kind of proxy they have. You can kind of understand the global coverage. And this is important to think about, in the same way that we were looking at the Climate Station network. Where do we have evidence from parts of the world? And more importantly, where do we not have evidence from various parts of the world, right? So, Brazil is not captured in this kind of thing. So anyway, they had 692 records from 400 or 648 sites, which is pretty different than what this group did, the Marcotte. So Marcotte actually used a synthesis of only 73 sites. However, they also chose those 73 sites as representative of biomes that were persistent from the Holocene forward, from 11,000-ish years forward. And that's really, really key too. However, it's messy. So this is the individual proxies that the Marcotte team looked at. So this is the individual data sets, and boy is it messy, right? The temperature anomalies, the black line, and the red line is the National Climate Data Center blended land and ocean data set. It's the one that we've looked at before. And so you look at all these different proxies that group was examining, and it's just fascinating, right? There is a lot of noise here. But again, you look for those general patterns that are the same. It's not always the same in magnitude, and that we understand that because, certainly some proxies are more sensitive to others, so they're going to show a stronger signal than something else. Like tree rings, right? It's going to be a much more amplified kind of response. with tree rings because you've got that really precise kind of measurement versus, you know, abundance of pollen. It's harder to say, oh yeah, it's absolutely a 3.5 degree, you know, departure. But you look at it and you average it all out, and that's where you get this general synthesis, which is really key. So yeah, you got lots of efforts like this. They're cool. You've got this data stewardship side, which means they're putting everything up online. You can go explore and click around and look at the data sets themselves, which is really cool. And what all this is doing, what's so important about the paleo ecology, is that it's giving us context, right? We can understand then the nature of the trend, the warming that we're seeing now. And that allows us to create figures like this, where we can say, yeah, for the last 20,000 or even the last 800,000, the thing that I was showing you last week, but certainly since the last 20,000 years, which is, you know, a good representation of our human habitation, right? Or a modern species human habitation. What we're seeing now and what we're forecasting. So this is looking at the paleo set, looking at that Marcotte kind of since the Holocene transition. And then we have even the A1B, the old emission scenarios. We're really in just totally uncharted, unmapped territory for this. And that's the crux of paleoecology is that it's helping us put some boundaries on understanding what this climate change we're experiencing is. You know, how does it differ in magnitude and in nature than past climate changes? And more importantly, what are the forcings? And that's really where we've come together and said, look, there's no other way to explain it. We look at these paleo records and we model, you know, what does the CO2 have to look like, and what does the ocean, the sea level rise have to, you know, what would it correspond to, and what does the record suggest? You know, when we account for sunspots, we account for Milankovitch cycles, we account for volcanic eruptions. We throw all those things in to describe the past climate, and we get really good at being able to predict what we see in the records. And then we try to forecast what's happening now, and we can't unless we introduce human released CO2. And when that synthesis came out, when they said, and again, there's this consensus of look, all these models, all these approaches to modeling are coming at the same result, same conclusion, that there's no way to describe the warming that we're seeing now without the inclusion of anthropogenically injected CO2 into the atmosphere. There's no other way to describe it. Accounting for all these things that we know have humongous impacts on climate, we can't describe what we're seeing now unless we introduce a human CO2 forcing. So that's where we're going to get into next week, when we started talking about processes and thinking about the carbon cycles and the hydrologic cycles and how these all play out, and what exactly has changed in the last 150-ish years that has caused just this tremendous spike in CO2, and what we're seeing is the temperature increasing as well.